you thinking as far as, what do you need to review from Chem 1A as well? And so, let me go ahead and grab the cards. And again, this is not worth any points. It's just a snapshot. I just want to get a snapshot at this point in time. Let's see. Maybe it's easy, maybe it's hard. Okay, can you put your name? You don't have a name? All right. You didn't put your name. It's okay. We'll do it anonymously. Can I get some more cards? Okay. I'll scan these later, but let me tell you. Thanks. Let me tell you what. So when you see something like calcium carbonate, just talking about Chem 1A stuff. Thanks. Put this over here. One thing is, can you tell me what the Lewis structure for calcium carbonate is? What would the Lewis structure of calcium carbonate look like?
It's an ionic structure.
It's an ionic structure, so ionic structures are different than covalent structures, right? And so for ionic structures, how would you describe that difference between ionic structures and covalent structures, especially in showing the bonds?
The ionics have the charge, and then the covalents you show sharing of electrons.
Yes, you show the sharing of electrons versus the charge, right? Do we show ionic bonds in Lewis structures? No. How do you show an ionic bond in Lewis structure? With the brackets, and you draw the ions right next to each other. So the Lewis structure for calcium carbonate would be the calcium ion. This would be the Lewis symbol, and then the carbonate. Well, the carbonate, is tricky because, yes, this is an ionic compound, but carbonate itself has covalent bonds. And what is the structure of carbonate? It's going to be...
Surrounded by the
Yeah. What's the shape, the geometry? Yeah. And we know about resonance, right?
Yeah.
And so actually, you could draw a single resonance form, which would be two singles and one double, or you could draw
Hybrid.
or the hybrid. You guys remember the resonance hybrid? Where all three bonds are the same. And so we'll just kind of draw the hybrid here. And the charge is...
-1/3.
Yeah, good. So that type of stuff you want to know. And so the carbonate is going to have a very nice trigonal planar structure, right? And so this is it, but is this the entire structure of calcium carbonate? Or what do you know about ionic compounds? Ionic compounds form molecules. Ionic compounds form lattices. So what should I do to show the lattice of this? Yeah, each calcium wants to surround itself with as many carbonates as possible, right? And so how many carbonates do you think I could fit around this? Well, maybe 4 in the plane, and then maybe 1 on top and 1 below, maybe 6. But I'd know the number if I knew what we call the crystal structure or the crystal lattice. You guys learned about some of the crystal lattices in Chem 1A. Do you remember some, like face-centered cubic and body-centered cubic and those? Well, there are more. There are ones that don't form a cube, and this is one of them. But anyway, we try to form as many anions around each cation and as many cations as around each, and then we generate a lattice, right? And so the actual lattice is, it looks like this. It's kind of an offset cube. It's because of these trigonal planar, carbonates stuck in there. which doesn't make it a nice cube. You know, this almost looks like a face-centered white, right? Face-centered cubic, doesn't it? With the carbonates in what we call the octahedral holes. Do you guys remember the octahedral and tetrahedral? Probably not. It's not so critical for Chem 1B. You know, for Chem 1B, this is just a little bit of Chem 1A, but this is the lattice. Now, the lattice for this, would you expect it to be very strong or not so strong? Strong. Why do you expect this lattice to be strong? The bonds are strong. The ionic bonds are strong. In order to pull off a carbonate, it's going to take some work. Why? Or pull off a calcium is going to take work. Because is that calcium just bonded to one single carbonate? No, it's bonded to a bunch, right? And it's held there tightly. It's held there tightly because, tell me from Chem 1A, because of strong electrical interactions. And chemistry, what do you guys know about chemistry? What's the most important force in chemistry? Electrical. In fact, chemistry is all electrical forces, right? And so back in chapter 1, they talked about Coulomb's law, I think, and electrical attraction. So you want to go back and take a look at that. This lattice is going to be strong because, I know it's going to be strong because calcium is a 2 plus and carbonate is a 2 minus. Although carbonate's kind of big. You see that? And so they can't get as close. The closer they are, the stronger the attraction. The further apart they are, the weaker the attraction. Coulomb's law depends on two things. What does it depend on? Charge and distance between the center of the charges, right? And so that means the strongest attractions will be between the highest charge and the smallest size. And so there's something called charge to size ratio. The greater the charge to size ratio, the more reactive or stronger you expect it to be. And so these are, people ask me, what should I review from Chem 1A? Well, these are the types of things you start reviewing from Chem 1A because we can use them in Chem 1B. We can use them because when we think about calcium carbonate, I purposely did this. Is calcium carbonate AQ or solid? Calcium carbonate's solid because it's, well, there are two things. One, you could memorize it. You memorize it. Carbonates are all insoluble except for group 1 and ammonium. Well, this is not, calcium is not group 1, it's not ammonium, therefore it's insoluble. That's memorization. But we want the two-pronged approach, right? We just don't want to memorize a whole bunch of facts. We also want to understand things a little bit more theoretically. And so trying to understand these, you can kind of predict that calcium carbonate probably won't dissolve, whereas something like calcium chloride probably will dissolve. Why? Because chloride is a -1, versus carbonate a -2. So harder to pluck the ions off. And so we think about that in terms, and so here, the first thing is, well, sulfuric acid, is that AQ? Sulfuric acids are going to be AQ. So if there's water present, aqueous, means there's lots of water present. If there's water present, and let's say, oops. Let's say I didn't specify. If I gave you sodium carbonate and sulfuric acid, and I didn't tell you the state of sodium carbonate, well, sodium carbonate is a solid, this white solid. Will sodium carbonate dissolve in water? Yes. And therefore, I would have written sodium carbonate AQ, whereas I would write calcium carbonate as solid. And so the first thing is calcium carbonate is a solid, even if there's water present, which there is. And then sulfuric acid, H2SO4, which is H. All right, now when I think of calcium carbonate, this is what I picture. A lattice, ionic lattice. Hard to dissolve. I'm going to have a lot of white PPT. Limestone. Think of limestone. What do you think when you think of H2SO4? Strong acids. Strong acids are? Yeah, so when I have an aqueous solution, the thing I think about is, yes, it's soluble. The next thing I think about are electrolyte properties. Strong, weak, non-electrolytes. And then I try to visualize what's happening here based on this. And so, thinking about a strong electrolyte like H2SO4, one thing is, there are different levels you can take this, but to properly review Chem 1A, then we should be able to whip out the Lewis structure for H2SO4. What does the Lewis structure look like for H2SO4? Now, H2SO4 is a very tricky one. Sulfur is the central atom. Okay. HO? What? The Lewis structure.
Sulfur is not there.
It's tetrahedral, good. Tetrahedral sulfur. You guys remember tetrahedral? What are the bond angles in tetrahedral? 109. Although this looks like 90, is this accurate? No, it's a Lewis structure, so we don't care. All right, what do you know about this? What you know about this is that H2SO4, I didn't spend that much time in Chem 1A, but some of the things that I kind of glossed over in Chem 1A, I'm not going to forget about them. We want to talk about them a little bit more in Chem 1B. And that is, what do we do with sulfur? Do we leave it in octet? What's the problem with leaving this in octet? Well, it seems like there's no problem. We have enough electrons to complete the octets of everything. Or is there a problem with leaving sulfur as an octet? Versus expanding the octet. We could expand the octet by 1 pair, or we could expand the octet by 2. If you look at sulfuric acid on Wikipedia, this is what you're going to see. On Wikipedia, you'll see sulfuric acid has 2 double bonds, like this, to the terminal oxygens.
You have to expand it to match the oxidation state.
I think Wikipedia. Last time I looked, which was a long time ago. Yeah, 2 double bonds. Why did they expand the octet on sulfur?
Formal charge.
Formal charge. Right? They wanted to reduce the formal charge. What are the formal charges? This for sure. If you forgot formal charges, well, maybe you didn't. It's hard to forget formal charges. If you forgot formal charges or oxidation states, you'll need to review those. Review those now. What are the formal? You should be able to tell me the formal charges immediately. Yeah, the formal charge on sulfur is. Okay, now with formal charges, how do we write that normally? Now there's a convention, and the convention's not set in stone either. And so this convention, you'll see some dark variance here, but the convention is the circulum. And so the formal charge would be +2, not 2 plus, +2. That would be the convention. What are the other formal charges? -1 on this and minus, and so we just usually write a minus and circle it, not -1, minus. What's wrong with that? Well, nothing's wrong with it except what does formal charge tell you? Tells you, somebody define formal charge for me. This would be on like a final exam question in Chem 1A. What's the definition of formal charge? Okay, yeah. It's a distribution of electrons, assuming that the bonding is 100% covalent. That's one way. And so if you look at the distribution, sulfur lost 2. Well, what's the problem with that? There's no problem with that. +2 we see all the time, but you know, you got to think about when something loses an electron, what energy comes to mind?
Ionization.
Ionization energy. Do you guys remember I1 and I2? What happened? When you go from I1 to I2, there's a big jump, right? And so it becomes much more difficult to ionize. And so sulfur losing 2 electrons, it can be done, but it's going to cost you energy. Versus expanding the octet. If we expand the octet, then we don't have to ionize I1, I2 of sulfur, right? But we'd have to expand the octet, which means what? Promoting electrons up into an empty higher energy orbital. And we know that we can expand, we can't expand the octet on all elements. We can only expand the octet on elements that have an empty D shell that's available, D subshell that's available. And so here we can expand it. And so the thinking goes, the cost of expanding the octet versus the cost of ionization, well, it costs less to expand the octet, so why not go that way? Nature's going to find the path of least resistance, right? And so you need to start reviewing that if it's not fresh, also in your memory. But this one is an advanced topic because what? What type of bond is this? Is that a PP pi bond? The double bond. There's an sp3, sp, what's the hybridization on this oxygen? This would be an sp3, sp2 sigma bond and a pp pi bond? Yes? No, if you, sp3 means you've hybridized all 3 of your p orbitals, which means it's not an sp3. It can't be a pp pi bond, right? It's got to be a PD pi bond. Have you ever heard of PD pi bond? Well, we need not just one PD pi bond, but we need 2. And at 109, and so there are arguments against expanding the octet here, you know, forming these PD pi bonds. And so what the reality turns out to be is this. It's like, remember resonance hybrids? Resonance hybrids is you look at hybridizing or mixing these structures into something. Well, it's kind of like that for this. You know, this is one extreme. This is the opposite extreme. The real picture is somewhere between. Now, the somewhere between, this is what we call a totally covalent compound. This is a 100% covalent compound because all the formal charges are 0. This compound has ionic interaction too, because not only do we have the covalent bond here, what kind of covalent bond is that? This is a sp3, sigma bond. Not only do we have the sp3 sigma bond holding these 2 atoms together, we also have an ionic bond because if this atom is negatively charged and this is positively charged, we have the electrostatic attraction between charged atoms. Do we show the ionic bond? No, we don't. We just show the charges, right? The charges next to each other. That's what holds these ions together. The opposite charges next to each other, right? And so there isn't any special line here drawn for an ionic bond, just like there wouldn't be a special line here drawn for an ionic bond. But we know that because of the separation of charge, there's got to be an electrical attraction, which is going to help. Now, what is a covalent bond? A covalent bond is also an electrical attraction. So we have 2 types of electrical attractions happening here. We got the covalent electrical and the ionic. And so in the end, if you go back to this chapter and review this, they talk about sulfuric acid. Sulfuric acid has a certain percentage of ionic bonding, a certain percentage of covalent bonding, and it's somewhere between these 2. It's more like this, where we have one kind of double bond type, single bond. Well, this is all done, you know, all this stuff, you know, guessing where it's going to be, you know, is formal charge the most important or is octet the most important? All this guessing is because we're doing this on pencil and paper, right? If we really wanted to get a more definitive answer, then how could we do this? Not by guessing, we would do a full what's the theory underlying bonding? What's the theory underlying chemistry?
Quantum mechanics.
Yeah, we would do a full quantum mechanical analysis of this to figure out, what is the percent ionic character in these bonds? How much D character is mixed in there? And so in Petrucci, in that chapter, I think chapter 12, talks about, from the quantum mechanical calculations, very little D character is found in the bonding here, which means a PD pi bond isn't a significant contributor to this. He said very little. He didn't say no D character. If he said no D character, then you'd expect nothing. No contribution, purely ionic, purely octet. Okay. Well, anyway, the chemistry builds on top of each other in steps. Do you see how it builds in steps? And you don't want the next step to be too large of a gap, because pretty soon you're going to be totally lost and not know what the person's talking about, right? And so we build. Chem 1A builds on this. And then Chem 1A builds on Chem 4. Chem 1B is going to build on Chem 1A. And so it's not like if it didn't quite click in Chem 1A, here's your chance. You can get it to click in Chem 1B. If it doesn't quite click in Chem 1B, then there's your chance you can maybe get it to click later on. But you want to pick it up little by little each time we go, so you don't have a big jump, a big barrier. And so these are the types of things, when you do, and this is why in a lot of exams they leave it open-ended. They want to see, how much can you tell me about this? They don't ask for specific. Okay, all I want is AB plus, CD gives you AD plus, whatever. But they'll start to want to, how much can you tell me about this? This is like oral exams. Oral exams, they never say, what is the answer to this? They're just going to tell me about this. Or how does that interact with that? And so in oral examinations, it's open-ended, because you're supposed to go, and then somebody says, okay, that's enough, stop. Hopefully, or you just sit there thinking, and it's dead silence. You'd rather have, okay, that's enough, stop, we've heard enough, than, okay, this is all my knowledge and it's nothing, with this. So, the Chem 1A stuff, we'll have a chance to reinforce that, but we know that this HO bond isn't so strong. And so I'll just draw the Wikipedia structure to this, because actually that's what you're going to see most. You're going to see this as an expanded octet, but you got to realize that this isn't set. This is the way I've always drawn sulfuric acid: 2 double bonds, 2 single bonds, expanded octet. But with the latest data, things change, and things are always changing. Does that mean the theory's bad? No, it's just, we're getting better and better computers, which can do more and more accurate calculations. All right, so what forms from this? All right, carbonic acid and calcium sulfate. Okay, carbonic acid, automatically you should know that this stuff is unstable. It's going to decompose into water and carbon dioxide. This is a gas. And calcium sulfate is a solid. Sulfate, like carbonate's a -2. -2 is probably a strong ionic bond. It's going to form a lattice like that, except carbonate's trigonal planar. Sulfate, you would expect to be tetrahedral. And so having a tetrahedral ion in here is going to, it'll probably be a cubic structure. It'll be like a cube rather than this distorted cube. Do you see it? And because the sulfates are going to be round rather than these flat triangles. All right. And so what is the driving force for this? The driving force there, I like this one because the driving force you can say in different ways. We're going from a stronger acid to a weaker acid. It doesn't have to be a strong acid, just stronger than what you're forming. And so I call that SA to WA, stronger acid to weaker acid. We're also forming a gas, and we have precipitation. And so this is kind of nice because all three, which means, you know, if you think about the driving force for this is going to be very strong. You have all these things going for this reaction. Now, the next thing we want to do, and you'll want to go back, is when we do the ionic equation, this is called the complete equation. When we do the ionic equation, what do? Yeah, we either ionize it or leave it alone. And so what do we ionize? Not all the aqueous ones. We just ionize the strong electrolytes. So is calcium carbonate a strong electrolyte? No. The strong electrolyte should be soluble. Now we have two definitions for electrolytes. Do you know what the two definitions are for electrolytes? When you're talking to somebody about electrolytes, you have to be careful. Because if you're talking to a person who works on batteries, they'll have a different definition than if you're talking to somebody who's working on sports drinks. You know? And so the two definitions of electrolytes are what? Do you guys remember this from Chem 1A?
One definition is ionizes 100%.
Yeah, ionizes 100%. And so using definition 1, some people will say calcium carbonate is a strong electrolyte, but it's not very soluble. In other words, the tiny bit of calcium carbonate that does dissolve breaks up into ions. And so you'll hear people say that. But, you know, if you took some limestone, put it in water, is it going to conduct electricity very well? And so other people will say, no way, calcium carbonate is not a strong electrolyte. Strong electrolytes need to conduct electricity as good as copper metal. And there's no way calcium carbonate mixed with water will. And so we have those two. We're going to use the definition. Does it dissociate close to 100%? No. Most of it's going to stay locked in a crystal lattice like this. And so we don't touch this. This is calcium carbonate solid. What about H2SO4? Yes, it's a strong electrolyte. So what happens with H2SO4? What happens is, do we get this? 2 H pluses plus a SO4 2 minus? No. Why not? Because the first hydrogen breaks off easily. And so H2SO4 is a strong electrolyte. That means that hydrogen is held on weakly. But once you lose the first hydrogen, then the second hydrogen is harder to lose because now we're trying to pull it off a negative species, make it even more negative. It's going to be more difficult. And so is this a strong electrolyte, HSO4 minus? No, it's a weak electrolyte. And therefore, we only dissociate one. So I wanted to review that there. H2O, do we dissociate that? No. CO2? No. CaSO4? No. And so it turns out that this is also, there are no spectators here, and so this is also the net ionic equation. This. All right. And so we would define the driving force here. Driving force 1, driving force 2, and driving force 3 in this particular way. All you need is, how many driving forces do you need for a reaction to occur? Only one. That's it. You don't have to have 3 driving forces.
So in this reaction, is calcium carbonate dissolving in the sulfuric acid in order to...
Yes. That's a good point. Calcium carbonate is dissolving in the sulfuric acid. You know, but the solubility rules aren't, will it dissolve in sulfuric acid? The solubility rules are, will it dissolve in water? And so when we do this, when we do the ionic equation, we're just looking at what dissolves in water and does it dissociate. We don't do the chemical reaction, so this is still physical, and then we do the chemical reaction. So we separate it. Obviously, it's all happening at once. You know, the calcium carbonate is reacting at one time with the sulfuric acid. Most ionic compounds are solid, liquid, or gas. Most ionic compounds are solid. So normally for something like magnesium nitrate, we would write solid. But if I have magnesium nitrate and I know there's aqueous ammonia around, then there's water. So even if I pour in solid magnesium nitrate into aqueous ammonia, that magnesium nitrate will dissolve in water even before reacting with anything. It could happen at once, but it's going to dissolve first. And so for magnesium nitrate, what I do in this case is, I know it's a lattice. It's nitrate similar to carbonate. It's going to have a trigonal planar structure. The lattice is probably going to look like this. Although not exactly like this, because we need 2 nitrates for every magnesium, so it has a slightly different crystal structure. But magnesium nitrate, we write AQ. Now AQ is so common that I usually skip writing it, and so if you omit AQ, that's fine. Now what about aqueous ammonia? I'll just write AQ. Versus gaseous. Ammonia is normally gas, but you know, there's a rule, solubility rule for molecular compounds called, does anybody know the solubility rules for molecular compounds? You could say it in one sentence. What is it? Starts with like. Like dissolves like. So ammonia is polar, water is polar. Ammonia is going to be very soluble in water. Whereas CO2 is non-polar, water is polar. CO2 bubbles out, effervesces. And so like dissolves, ammonia is really soluble. Does this look like a metathesis reaction to you? No, it doesn't, because I see magnesium ions, nitrate ions, but ammonia I don't see any ions. And so for ammonia, what do you do? Well, ammonia is a weak base. Weak bases hydrolyze partially to form ammonium ions and hydroxide ions. And so we form some ammonium hydroxide by the partial hydrolysis. The thing about this is, why don't I just cross this out and write ammonium hydroxide? Because it's ammonium hydroxide that's actually reacting, isn't it? And so shouldn't I just go ahead and X this out and replace it with ammonium hydroxide? It's metabolism. Okay, why not? Okay. Any other? Well, it does do that. Ammonia will collide with water and form ammonium ions and hydroxide ions. So it does it. Huh? Yeah. Yeah. It doesn't completely hydrolyze. It's unstable. It's in very small concentrations. And so basically it's this. When you go to the chemical supplier and order this, I'm going to order a bottle of this. Are you going to order a bottle of ammonium hydroxide, this byproduct that forms a little bit and is quite unstable? Or are you going to order a bottle of aqueous ammonia? You're going to order a bottle of aqueous ammonia knowing that one of the byproducts in that bottle is a little bit of ammonium and a little bit of hydroxide, which we can use to do a metathesis reaction. And so the reason we write this, we leave it as ammonia and water and not ammonium hydroxide. It depends on your Chem 1A instructor. You know, they have their reasons. A lot of Chem 1A instructors say, you know, that's ridiculous. It's ammonium and hydroxide that's reacting. Let's leave it as ammonium and hydroxide. But you know, convention is that, you know, we buy this off the shelf. So you look for it. You got to be careful with ammonia, because I was looking at in a European catalog for ammonia, and it wasn't called ammonia. Do you know what it was called? I couldn't believe it. They didn't have ammonia. How can they not have ammonia? And I realized it didn't have ammonia because they called it something else. Do you know what they called it? Nitrogen trihydride. So when I looked for nitrogen trihydride, it was there, and I could order it. For water in that catalog, they might not call it water. They might call it dihydrogen monoxide. Maybe. No, I don't think so. So you got to be careful because those nomenclature rules can be tricky. Well, anyway, the reason why here we leave it like this again is because this is what we buy. But when we do the reaction, we want to put it like this. So it's an AB plus CD pattern to give us what? Magnesium hydroxide and ammonium nitrate. Wow, we're forming ammonium nitrate. Some of you might know one of the chemical properties of ammonium nitrate. What is that? Chemical property of ammonium nitrate.
It's very combustible.
Yeah, it's very combustible. It's actually, you don't even need oxygen to combust it. It's explosive material. But will it explode in this case? No, because you need big collisions between the ammonium and nitrate, and when it's in aqueous solution like this, it's not going to happen. The maximum temperature of an aqueous solution isn't going to be, much more than 100 degrees. And so that limits the amount of kinetic energy you can have. But what some people do is they accidentally boil off all the water. They boil off all the water, and they're left with some solid ammonium nitrate, and then they just keep heating it hotter and hotter. And then you have potential risk there, right? And so this is it. The other reason I spend a lot of time, more so than a lot of other instructors, is my personal experience with my understanding of chemical reactions, but also with working with students. A lot of students totally ignore chemical properties. And this has happened in Chem 1B. In Chem 1B, I've had 3 explosions happen by the students. Students mixing, and it was, I guess it was my fault too, because I had people making up a lab. I had people making up a lab in which they were using a powerful reducer. In the current lab, we were using powerful oxidizer. If you take a powerful reducer and powerful oxidizer, what are you going to get? Violent reaction, right? And so I told the student, make sure you don't mix your waste with this waste. But, with the pressure and time and everything, the student poured their waste which is powerful reducer, ethanol, into the powerful oxidizer, which is nitric acid. And boom, that hood right there was it. And so then I thought, my experience was I finished Chem 1A and Chem 1B not really understanding chemical reactions, and that shouldn't happen. I spent way too much time talking about physics. When I was at Santa Barbara City College, I talked, and so I had a Russian student. The Russian student complained to me, "Your class is just like physics. Where's the chemistry?" And so this is it. You got to have some factual knowledge memorized. And hopefully we'll see patterns and get some theoretical knowledge out of this stuff.